We're going to be talking about models of the atom. So J.J. Thompson in 1897 had discovered the charge to mass ratio of the electron. He knew that there was a particle that was pretty charged negatively and called it the electron, but he didn't really know how atoms worked. He thought that the plum pudding model was the model where basically you had these little plums, which would be the electrons that were just distributed throughout the whole atom like plums in pudding. It wasn't until 1911 that Ernest Rutherford did his gold foil experiment that we started to understand a little bit about which particles are where in the atom. So Rutherford shot alpha particles, draw like this little fish-looking thing, at gold foil. So you probably need to know what those two things are. An alpha particle is a helium nucleus, and a lot of radioactive isotopes will give off these alpha particles. It's one of the main things that comes out when something decays. It's 2 protons and 2 neutrons. So it has a mass of 4, charge of +2. So they're positively charged, and he decided to shoot them at gold foil. Now gold foil, kind of like aluminum foil, just what the rich kids wrap their sandwich in. It's just a few atoms thick piece of gold. Well, sometimes the alpha particles would just go straight on through. He had this fluorescent screen that was kind of curved around it so that he could detect, because when the alpha particle would hit it, you could see it fluoresce. But occasionally it would be deflected, and sometimes they were deflected at like extreme angles too. So Rutherford kept shooting the alpha particles at the gold until he was able to figure out what percentages were being deflected. And he realized that most of the atom was empty space. Most of the time, it just went through. And that's kind of what he expected, because he was kind of thinking like the plum pudding model. But when something would get deflected at an angle, he was really shocked by that. He said it was kind of like shooting a cannonball at tissue paper and having it bounce back. It's actually kind of like shooting an alpha particle at gold foil and having it bounce back. But it was surprising to him regardless. Well, that's because the nucleus of an atom is tiny, and that's where almost all the mass of the atom is located. I've heard it said that if you had a carbon atom and you made it the size of like a US Bank Stadium, that the nucleus is like a breadcrumb on the 50-yard line. So it was seldom that we would actually hit something like a nucleus and have it bounce back, but the fact that an alpha particle would bounce back would tell you that the nucleus is positively charged, it has most of the mass, and it's very small. So he used this experiment to come up with the nuclear model of the atom. So we have protons in the nucleus, which are massive, 2,000 times more massive than electrons, and then electrons orbiting. But there was a problem with the nuclear model of the atom. The problem is, if you have an electron orbiting out here around a nucleus, that electron would have to be accelerating, because to not go in a straight line is to accelerate. Well, we already knew that any accelerated charge gives off light, and atoms don't give off light all the time. So how could these electrons be orbiting and not giving off light? A accelerated charge is a changing electric field, which produces a changing magnetic field, which produces a changing electric field, and we're making electromagnetic waves. So Rutherford's model was not quite complete in understanding how atoms work. Around the same time that Rutherford was making his discovery, they were also studying the spectrum given off by gases that were fluorescing when electricity was sent through them. So here I have hydrogen gas, and it kind of looks like a pinkish color, but if I send it through a diffraction grating, you can see that there is a violet and a blue and a green and a pink that are making up this spectrum. It's a little hard to see on the phone, but they studied the wavelengths of those light given off by the hydrogen atoms, and they used that to help make a model of the atom. Each gas gives off different spectral lines. So this is neon.
you can see that neon has many more lines. For some reason, we're struggling to see the ones in the blue and the green areas, but there are many, many lines given off by neon. So it's kind of a signature of the atom and where its electrons can be that tell us about the spectral line. Scientists began to conclude that something about the electron energy levels and the transitions between energy levels must correspond to the particular frequencies that an atom can give off. I'm going to talk about an energy level model of the atom. So Danish physicist Niels Bohr said, we know that the electron is attracted to the nucleus, and the main attraction is not gravity, like a satellite orbiting the Earth, but the electric attraction. So we can think of the centripetal force as being Coulomb's law, K, Q1, Q2, over R squared. That's what's causing the orbit. So we'll set that equal to centripetal force, which, if you remember, is mv squared over r. M is the electron, the mass of the electron, the thing orbiting. So r is going to cancel. Well, it turns out that both the electron and the nucleus, if this is a hydrogen atom, have the same charge. The nucleus is +1 and the electron is -1, but the charge of an electron is actually 1.6 times 10 to the negative 19 coulombs. So I'm just going to use the letter E for that for right now. So I can simplify this to say K E squared, since they're both the same charge, divided by R equals mv squared. Well, if I want R by itself, it's K E squared divided by mv squared. All right, so this is kind of how Bohr started with trying to find the radius of that electron orbiting the nucleus. Well, one thing that we knew from Broglie is that you can calculate the wavelength of any object that has momentum by just saying that lambda equals h over mv. Well, what Bohr said was these orbits need to have an integer number of wavelengths in order to be a stationary state. In other words, if only a half a lambda fits on a circumference, or 1.5 lambdas fit, it will destructively interfere with itself and it won't be a stationary state. So in order to be one of the allowed orbits, if the atom is really quantized, then it needs to be n lambdas, n of these, around the circumference of that orbit. So 2 pi r, that's a complete circle, must be n h over mv. Right, so if you think of the wavelength of a wave, so, you know, if you have one complete wave, can't really see that over there, the wavelength from that wave needs to be exactly around the circle. So this one would be a little short, right? Or maybe you could fit 2 waves around the circle if you put 2 in for n. N is an integer. So if I solve this for v, I'm going to get n h over 2 pi r mass of the electron. That is what Bohr put in for, draw this down to here, for v. So r is going to be equal to k e squared divided by that stuff squared. So we can say v squared is n squared h squared 4 pi squared r squared mass of the electron squared. Right? Well, since we're dividing by it, everything that's downstairs in this equation needs to come upstairs in this one. So we're going to say 4 pi squared r squared mass of the electron squared. And then we also had divided by n squared h squared. And then in our original equation, we still had mass of the electron down there. Okay, so this squared is going to cancel with this mass of the electron, and this squared is going to cancel with this r, which is going to make this 1. So if I want to get the radius by itself, it looks like the radius by itself
see if I can see that over there, is going to be equal to n squared h squared divided by k, Coulomb's constant, 9 times 10 to the 9th, e squared, that's the charge of the electron, 1.6 times 10 to the negative 19th coulombs, 4 pi squared r, there's r is canceled, isn't it? Mass of the electron. A lot of letters in there. All right, so what is that radius? Well, if you put all those numbers in, so let's just put 1 for n, because we'll just find the first energy level. We put 6.626 times 10 to the negative 34th for h, 9 times 10 to the 9th for k, 1.6 times 10 to the negative 19th for e, 3.14 for pi, and 9.11 times 10 to the negative 31st for the mass electron. Bohr calculated the radius to be 5.3 times 10 to the negative 11th meters. That's where the electron is from the nucleus. Or, I think it's 0.053 nanometers. So now we know the first energy level's radius. All right, so we know that the closest radius that we can have our electron at is 0.053 nanometers, but it can be at different radiuses, which Bohr called energy levels. So what Bohr wanted to study was the energy associated with each of those levels, because he knew that if you excite an electron and it jumps down a level, it's going to give off a photon that corresponds to that jump. So if he knew the energy of each jump, he could see if the photons had those exact energies. You know, using E equals HF. You could see if E initial minus E final, the change in energy, is equal to HF for the different photons that he had observed for hydrogen. So if you have something orbiting a nucleus, it's got both potential energy and kinetic energy. It has potential energy, we call it electrical potential energy, that is negative because you would actually have to give it energy to escape, right? It's bound to the nucleus. And it has kinetic energy because it's in an orbit. So the equation for that, I'm not going to prove this to you, is negative k e squared over 2r, where e is the charge of the electron. We have a similar kind of equation for like a satellite orbiting. They have negative potential energy and then they have positive kinetic energy, but their total energy is negative. So the electron has total energy that is k e squared over 2r, and it's negative. So when Bohr looked at this, if you look at the equation for energy, you can see that everything's a constant except for r. And if you look at the equation for r, you can see in that formula, every single thing is a constant. H is Planck's constant, K, Coulomb's constant, E is the charge of electron, that's constant, pi is a constant, the mass of electron is constant. So everything's a constant in that except for n, and n is squared. So he thought, I want to write the energy in terms of n. So the energy in terms of n is negative 2.17 times 10 to the negative 18th joules times 1 over n squared. Right, well, that's such a small number of joules that it's going to be helpful to use electron volts. So if you convert this, you know, divide by 1.6 times 10 to the negative 19th joules per electron volt, you're going to get negative 13.6 electron volts times 1 over n squared. So for the first energy level, n equals 1, you could calculate the energy, just put 1 in there, and it's negative 13.6 electron volts. That's how much the electron is bound to the nucleus with. So in other words, if you want to ionize hydrogen, set that electron free, you need to give it 13.6 electron volts to set it free. So the most tightly bound that our electron can be to our nucleus is with 13.6 electron volts, meaning that it takes 13.6 electron volts to set it free. Right? If you get to a higher energy level, you're less tightly bound to the nucleus. That would be like if n equals 2 or n equals 3. So n could be any integer, 1, 2, 3, 4, 5, 6, and this is what we call the principal quantum number. It's like the first fundamental thing that we know about the electron is what's the energy level. And it's an integer. So level 1, called the ground state, n equals 1. Right? So you get an idea why the energy is quantized that comes from atoms now. But one thing that a lot of people don't realize is that the energy levels are not equally spaced. Right? The orbits aren't going up by equal amounts because they depend on n squared, and conversely the energy depends on n squared. So in other words, level 3 is not the same gap that there is between level 1 and 2 in energy. That gap isn't between level 2 and 3. 3 is closer to 2. Right? And then 4 is even closer to 3. And 5 is closer to 4. 6. Right? So the biggest jump you can make is down to level 1. So if you study hydrogen, and you look at the jumps that you might make down to level 1, like from 2 to 1, 3 to 1, 4 to 1, these jumps usually give off UV light, higher energy light, because they're bigger jumps. Where the jumps to level 2, right, from 3 to 2, 4 to 2, 5 to 2, give off the visible light, the spectral lines that we saw. And if you want infrared light, we're looking at the jumps down to level 3. So these series, we call them the Lyman-Balmer-Paskin series. The Lyman is the UV jumps, the Balmer is the visible, and Paskin is the infrared. We know exactly what photons are coming because we know the energy for every single energy level just depends on n squared, where n is the principal quantum number. Right? There are more quantum numbers about electrons besides just their energy level. You learned in chemistry that they also have orbitals, s, p, d, f orbitals, where s is 0, p is 1, d is 2, f is 3. This is what we call the second quantum number. Sometimes it's called the angular momentum quantum number. And it can be any of those, right? It has to be n minus 1. So in other words, if you're in the first energy level, you're never going to have a p orbital, but you can have an s. If you're in the second energy level, you can have an s or a p orbital. So it can be n minus 1. But that's our second piece of information that we might want to know about an electron in quantum mechanics. And then there are two more quantum numbers, which I'll mention briefly. We give the letter L for the second quantum number because angular momentum's symbol is L in physics. The third quantum number is the magnetic quantum number. So we're going to give that the symbol M for magnetic. And it can be L or negative L, or it can be any integer smaller than L. So like if L is 0, then your magnetic number is just going to be 0. But if L is 1, your magnetic number could be negative 1, 0, or 1. Right? If L was 2, you could be negative 2, negative 1, 0, 1, 2. If L was 3, it could be negative 3, negative 2, negative 1, 0, 1, 2, 3. So it can be any number, negative or positive, up to L. And then we have the spin. That's our final quantum number, which we're going to use S for that, S for spin. And that is always going to be either positive 1/2 or negative 1/2. Right? So when I think of electrons, I think of them as having like these 4 quantum numbers that are kind of their address. And N tells me their energy level. You know, what row of the periodic table are you in? Their L tells me about their orbital. Are you an S, P, D, or F orbital, like subshell within that particular energy level? The magnetic quantum number tells me about the orientation of the orbital. Right? You can, like the P orbital kind of looks like a dumbbell. You can orient that in different directions. And then the spin for the electron within that orbital is either going to be spin up or spin down, positive 1/2 or negative 1/2. And there's a rule, it's called the Pauli exclusion principle, that says for these 4 quantum numbers, N, L, M, and S, no 2 electrons can have the same 4 quantum numbers. They can't be in the exact same state, right? So if you got 2 electrons in the S orbital, there's going to be one spinning one way and one spinning the other way. They aren't going to have the exact same address, no 2 electrons, right? And it's the transitions that electrons make that give us the spectral lines that we see, the specific photons that atoms can give off. The Bohr model was very successful at describing the hydrogen atom and predicting the spectral lines of the hydrogen atom. But as we got to more complicated atoms with more spectral lines, we needed a little bit more complete picture of the atom. So in 1926, Austrian physicist Erwin Schrödinger came up with the wave model of the atom. He wrote a wave equation that described the 3-dimensional movement of an electron, and it's a very complicated equation, so I'm not going to even put it up here, but he called the wave equation psi, and it really described everything about an atom's electron. If you square psi, you get the probability of finding an electron at a point in space, which is really what quantum mechanics is about. So instead of thinking of it as energy levels, he thought of it as an electron cloud, which is probably a term that you've heard before. And for example, the Bohr radius, which we calculated where the electron is in the first energy level for hydrogen, that is the most probable location for an electron. If you calculate the largest value for psi squared, it's going to be at the Bohr radius. So that's where it's most likely to be when you're not looking. But it is a wave of potentials. There are many places that the electron can be, and understanding atoms is more about understanding the probability of finding an electron at a given place. So the wave equation tells us everything about the electron. And as we add together more wave equations, we get the probability.